Hello, my people. I hope we're doing well today. What we're going to be doing is we're going to be extending our application of trigonometric concepts beyond right triangles. So we've been doing trigonometry with respect to right triangles, and then we moved on to analytic trig. And now we're going to see how trigonometry helps us to evaluate and sort of give us perspective on triangles that do not contain a right angle. These are otherwise known as oblique triangles. So if you ever hear that terminology, it's referring to triangles like this. Okay. This does not take us too far afield because here's the thing: if I have this oblique triangle, I can always drop a perpendicular down and create two right triangles. I can subdivide it, right? If there's one of those instincts that should have been a takeaway from geometry, is that when you can't figure out an object, you need to start drawing more lines, and you need to start subdividing it. Now, once we have this powerful tool of trigonometry that allows us to evaluate right triangles, all you got to do is chop stuff up, okay? And here's what we're going to do. Basically, what happens is you do this enough times in order to solve the triangle. And by solving the triangle, we mean get a value for sides A, B, and C, and get a value for angles A, B, and C. But like all formulas, if you go through a process enough times, you want to sort of cut out the middle step, or cut out those first couple of steps, and just sort of turn it into a formula. But despite that fact, we're going to go ahead and actually show you where it comes from. Let's go ahead and call that altitude h, largely because A for altitude is already taken by side A, okay? Now, let's look over here at angle A. Now, angle A has an opposite of h and a hypotenuse of C. So if I say sine of angle A is equal to opposite over hypotenuse, okay, then h is equal to C sine A. Let's go ahead and do it for angle C over here as well. And if I have sine of C is equal to h over A, then h is equal to A sine of C. Well, if those are both equal to h, then they're equal to each other. And what does that look like but the step after having cross multiplied? So we can actually take that and turn it into sine A over A is equal to sine C over C. Now, if you're wondering where B is, you can do the same thing for B. You just have to, turn the triangle around and drop an altitude this way, or turn it around and drop an altitude this way in order to take into account and just basically have a different h, right? Because in any given triangle, there are three perpendicular altitudes that you can actually do. And what happens is basically we wind up getting sine A over A is equal to sine C over C, which is equal, predictably to sine B over B. Now, of course, you don't set all three of those equal to each other at the same time. You basically use whichever proportion actually winds up, if you're given information where this proportion is helpful, you use that one. If you're given information where that one is helpful, you use that one. If you're given information where that one is helpful, you use that one, okay? Now, you're wondering maybe, well, what about those obtuse triangles? Okay, because basically the problem is here is that when I drop an altitude for this particular problem, for this particular triangle, it is outside. It is outside of the triangle. And if this right here is A, then this right here is its supplement. So 180 degrees minus A, or pi minus A. Okay, well that's still h. Now opposite angle A is A, okay? Opposite angle B is side B, and opposite angle C is side C. Well, let's go ahead and, kind of play around with this just a little bit. I notice that sine of 180 degrees minus A is going to be H over C, right? Well, that basically means that H is equal to C times sine of 180 degrees minus A. Now, remember that when you're dealing with sine, if you were to just think of the graph. If you were to shift it by pi, which is half of its period, and then reflect it, which is what that actually entails, because of its period and because it's odd, basically what happens is H simplifies out to sine of A anyway, and so basically it holds just because of the properties of sine. Okay, so basically I just wanted to show you, just in case you get to get going along and kind of go, well, what about that obtuse? Well, this is the justification for it. I'm not going to finish that off, but if you have any questions on that, I guess I can attend to it a little bit later as well. So basically what we've done is, instead of dropping that H value, instead of dropping that altitude every single time I have an oblique triangle, we've created a formula which basically cuts out the need to do that, okay? Because you would basically drop that H value, and you would drop that altitude, and then you would get, you would get the values that you can get, and then you would set them equal to each other. Well, all the formula does is just, it sort of skips ahead and does the setting equal to already before you even get started, okay? Now, the way that Larson, which is the pre-cal text that I sort of screenshot this from, it has it as side, A over angle A, B over angle B, C over angle C. But of course, when you're dealing with proportions, you can reciprocalize those proportions, and it winds up being the same relationship. So it shouldn't matter, okay? All right, well, there is something that's a little bit strange about the law of sines, but I'm not going to introduce that now. Let's go ahead and work a couple of problems first, and then I'll show you how things get weird. Sound good? All right, let's say that I have the triangle given here. Okay. Now angle B is 40 degrees. Angle A is 81 degrees. And here's the thing. I mean, basically you can go ahead and figure this out. That winds up being 121, which is 59 shy, okay? 59 shy of 180. So you know that that third angle is going to be 59 degrees. Now you already have side B at 92. All you need to do from here is basically just set up proportions, okay? And so let's say we have sine of 81 degrees over A is equal to sine of 40 degrees over B. Now B, of course, B actually has a value. Well, okay, let's go ahead and cross multiply, the easier thing probably is you can basically reciprocalize these, and in doing so, that's supposed to be 81 degrees, and so A is equal to 92 sine of 81 degrees over sine of 40 degrees. Now, we have been dealing with radians for so long that when we get to law of sines and law of cosines, we're switching back largely to degrees. So you have to make sure that your calculator is actually in degree mode. Okay, and so we'll go ahead and quit. And what we want to do here is, now that we're in degree mode, let's go ahead and evaluate this. We get 92 sine of 81 degrees over sine of 40 degrees. And what we get is 141.364. Okay, remember, always to 3 decimal places. So that's 141.364. Now the only thing left to get is our C value. And you have now two complete ratios. What you're going to need to remember is when you have a choice, always use an exact value. So don't take, and I'm going to go ahead and do this upside down since I didn't think ahead last time. If you have this, don't set it equal to A over sine A, because that's an approximate value. Set it equal to the exact value so that you are as close as possible when you wind up doing the evaluation in your calculator and getting a decimal approximation. Okay, and so C is going to be equal to, well, let's go ahead and check it out. Okay, let's do this. Go 92 sine of 59 over sine of 40, and that's going to be 122.683. Okay, 122.683. Now, just take a moment and make sure that these make sense, okay? You know from geometry that the smallest angle is going to be opposite the smallest side. 92 is the smallest side, smallest angle. Largest angle, largest side. Middle angle, middle side. Okay, that's probably good stuff right there. All right, let's do another example. Alrighty. Well, here's the thing. When you're dealing with the law of sines, you have to have information that creates a complete ratio, at least one complete ratio. Because if you have a proportion and you set two ratios equal to each other, but they both have an unknown inside of it, you're stuck. You can't really go anywhere. By the way, that's why there's also a law of cosines, and we'll get there on Wednesday. But basically, you need A right here. Since this is the only side that is given to you, you need A in order to have a complete ratio. Well, the thing is that A actually is given to you. A is actually given to you implicitly because you have the other two angles, right? And of course, if you just, if you don't trust doing it in your head, 82 and 54 make 136, and the difference between that and 180 is 44. Okay? So you do have a complete ratio. You have the A ratio. Now you simply need to use that A ratio to get B and C. So you have 16 over sine of 44 degrees is equal to B over sine of 54 degrees. And you have 16 over sine of 44 degrees is equal to C over sine of 82 degrees. Okay? And then, so, like I said, you're going to use the exact value ratio in order to find what's missing. And so basically what you get here is you get B, 16 sine 54 degrees, all of that over sine of 44 degrees, and that you can plug into your calculator and get a decimal approximation. This one winds up being 16 sine 82 degrees over sine of 44 degrees. Again, another thing that you can plug into your calculator and get a decimal approximation. Now, let's go ahead and do that. Okay, so we have 18.634 and 22.809. So B is 18.634, so 18.634, and C is 22.809. Again, always to 3 decimal places. Always, always, always. And so, this basically winds up getting pretty predictable as long as we have no problems thrown into it, okay? Now, there are, every once in a while, problems thrown into it. But let's do one more example. And I basically on the first two gave you the triangle, okay? I won't be doing that on quizzes and stuff like that. You ought to be able to construct your own triangle. And here's the thing. Your triangle that you draw doesn't have to be to scale, right? Okay, so let's go ahead and just take the information that we have. I have 50 degrees. I have 62 degrees. Now that's 112 together, okay? Now 112 is 68 degrees away from 180. So, and we have A is equal to 4. Well, let's just go ahead. And here's the thing. I mean, it's 50, 62, and 68. It's not an equilateral triangle, but it's close enough to where if you kind of draw something that's equilateral-ish, right? And the thing is, like I said before, it just has to be a graphic that allows you to to visualize what's going on, okay? This right here is 50 degrees. This right here is 62 degrees, and this right here is 68 degrees. A is across from angle A, B is across from angle B, and C is across from angle C. Now here is my full ratio. I'm going to use this ratio and set up a proportion with it and B, and then set up a second proportion with it and C. And I'm going to get B over sine of 62 degrees is equal to 4 over sine of 50 degrees. And then I'm going to get C over sine of 68 degrees is equal to 4 over sine of 50 degrees. Now, all I have to do is multiply both sides by sine of 62 degrees, and I get that, and I can find my decimal approximation. Same thing over here with C. I'm going to multiply both sides by the denominator on the left in order to get a complete ratio that can be plugged into my calculator and evaluated and approximated. And boom. Okay, 4 sine of 62 degrees over sine of 50 degrees. And then we get 4 sine of 68 degrees over sine of 50 degrees. Boom. Okay. And they're all but they're both between 4 and 5 because the angle measurements are not that far off. It's not like, 20, 30, and then 130, right? They're all sort of in the 50 to 70 range, and therefore it shouldn't surprise us that the disparity between the lengths of the sides is not that much. But what we get here is B is 4.610 and C is 4.841, and those, despite the fact that they're all really close in value, do make sense because you still have the smallest side opposite the smallest angle, the largest side opposite the largest angle, and the middle side opposite the middle angle in terms of its measurement, okay? Now, this is probably a pretty good place for us to stop for video 1 because in the next videos where we're going to discuss when things get weird. If you have any questions on the construction of the law of sines or on the first few problems, please do shoot me a message or an email. Messages are usually better. I check Teams a little more often over the summer than I check my email, as some of y'all have actually figured out. But yeah, reach out if you have a question, and I will be more than happy to answer it. Bye.